Yeah, J and C, jump, not carry. So if not carry, or if carry flag is 0, carry flag is reset, then it perform the jump. Or here jump carry, if carry flag is set, then it do the jump. Otherwise not. So it's like that. So these are the things are called conditional. There are few other things are there, conditional jump instructions. And branching structure, you know, like in our program, sometimes we can write if something is okay, then do this. Okay, this is called if then structure. And there is also some loop structure. Already we use the loop, but just formal discussion, like repeat something until for example 5 times we want to make a loop. We set a counter and we repeat, do the repeat. Or it can be like while do also. If while it is like that, then do this thing, something like. And applications using the loop and branch software structure, we'll see details. Okay, now look at here. So conditional jump, unconditional jump. For example, this is this one is the part 1 of a program. This one is part 2 of a program. This one is part 3 of a program. So here it is, the label is AA, for example. So in a part 1, after few lines, there is an instruction jump AA. That means it will, when actually it come here, it will jump and come to the AA level. So that means part 2 is skipped. It is overlooked. So this part is untouched. Okay, due to this unconditional jump, some part of the program will be untouched. You get my point? Is it okay? So what is called unconditional jump? Okay, so that means yeah, and what is the instruction mnemonics, or what is the code, I mean opcode, JMP? It is called jump mnemonics or jump instruction. And during this jump instruction, some part is skipped, is overlooked. Okay, so this is very normal. But what about the conditional jump? If you look at the conditional jump, yeah, conditional jump. So for example, this is part 1, and then you have part 2, and then you have part 3, for example, just for giving idea. So now in part 1 you say that jump JCC, I mean jump conditional. I mean if JCC kind of, for example, actually there is no instruction JCC, like JNC or JC only, jump carry, for example. So if it is so if the condition is fulfilled, then actually if the condition is not fulfilled, if condition is not fulfilled, it will go to the next line. If condition is fulfilled, condition made, if it is yes, then it will come to this label. Where is this label? For example, the label is in the part 3. It will come here, and then go move on to the next line, so on. So that means the part 2 will be overlooked if the condition is made. If it is not made, then it will move to the I mean from part 1 to move to the next line. That means in the part 2. Is that okay? Do you understand this one? Is it okay? Yes. So it's called that. Yeah. Yes. Okay. So it's called that conditional jump. That means some condition will be checked. If it is fulfilled, then it will skip something, I mean, it will it will do a jump. When actually there is a jump, that means some immediate some instruction they will be skipped. But when condition is not met, it will go to the next line. This is the things. Already we use it in some program. Okay, now look at here. There are some jump instructions in assembly language. One is called JA, jump above. I mean, something is, if you compare, for example, A and B, and if A is greater than B, if jump above, or jump above or equal, or jump below, or equal. So these are the things actually, I mean, so we didn't use so far. But this one is we use jump if carry. Yeah. So if carry flag is set, then do the jump. And if jump JCXJ, if CX register is 0, then do the jump. Okay, and then jump equal. If to compare, if you compare two number, if they are equal, do the jump. What is JC? Jump if carry. You know, this one is, we already use it, right? In finding the minimum, maximum. JC, jump if carry flag. For example, if you compare A and B, so A minus B, if B is greater than A, there will be a carry, right? So if there is a carry, then it will do the jump. Yeah. So and JE equal, if two numbers, if you compare, for example, if they are equal, it will do the jump. Okay, so the same way like jump greater. No, this one actually, JC, we use this one, JC, and there is another one, JNC. You either you use JNC or you use JC, because it depends on your logic, you know. So yeah, not JMC, not JMC, JNC, not carry. Jump if the if carry flag is 0, or jump if yes, JNC. So sometimes we use JNC. It depends on your logic, you know how, because a program we can write different way. So different way, but if as long as logic is okay, then it is okay. So maybe, for example, you use JNC. Someone may use other way. Like if you, for example, if you compare AL comma BL, but other one use compare BL comma AL, then the opposite thing you have to use. You get my point? This is the thing. And then yeah, so you don't have to memorize, but mostly actually we use, what are the things actually mostly we use? We use like these are the, like jump carry, jump equal, and then what are the other things there? Yeah, jump not carry, jump not equal, then yeah, jump not 0. Yeah, so far actually it's not like you have to memorize. It's about, like, you know, if you use it again and again. So I marked here, because these are the things we mostly use. So I mean, you will see quite often these things: jump 0, jump not 0, jump carry, jump not carry. These are the things so far. Okay, it's not you have to. It is not like you have to, I mean, blindly memorizing. Okay, now about if then structure. So in our program, sometimes our structure is, if it is, then do this. Like for example, if you compare AX comma BX, so you are comparing between AX and BX. So then you check a condition check, the jump equal. If they are equal, it will come here. Where actually a label equal. For example, label is here. You can see equal, under the equal label. These are the lines there. So these are the lines are there under the equal. But if it is not, you will go to the next line, right? If not equal, then you will go to the next line. Okay, now that means this is a kind of if then structure, because if ax is not bx, you will come to this line, but if ax equal to bx, you will come to this line. Actually, next instruction is if x bx. So that means it is kind of if then. If it is, then do this. Okay, so this is called if then structure. But there is another structure, for example, and al comma 04h. You know, 04h means we actually are interested about. So 04 means 0 0 0 0, and then 4 0 1 0 0. So actually we are interested about this bit. Actually, this is b3, b2, b2. So if we do the AND operation, al comma 04, that means all the bits will be 0, only this one will be what it is, because with n, I mean it is the AND operation with 1. Okay, so that means we are interested about b2 bit. So then what actually said, jump not 0. If this one is not 0, it will come here in this line. If it is 0, then it will go to the this line, next line. So that means next instruction, this line is the next instruction if b2 of al equals 0. If b2 of al is 1, then actually basically it will come here. This is also kind of if then structure. It's okay. All right. So then there is another kind of structure. The same thing. If then structure again. Look at here. Actually, these are the things already we use, but just formal discussion. Move cl comma 03h, and then shift right al comma cl. That means 3 times actually you will do the shift operation of al, and then actually what happened? If you do the 3 times al, so it's about the al. So look at here. For example, al is 8-bit register. Okay. This is our al, right? So if you do the 3 times operation, what happened? This bit, for example, this is 2, and this is 2 0 1 2, and this one is 7. So if we do the 3 times right shift, what will happen? This one will one shift, it will come here. This one, it come here for one shift right. Then 2 shift, it will come here. Then 3 shift, it will come out, right? It will come out. So 3 shift, it will come out, but it will fill up the carry flag. If you can remember in the shift operation. So that means then it will fill up the carry flag also. Then we check. So that means 3 times we will do the AL a shift rotation of AL, and then we check the carry flag. If jump carry, that means if carry flag is 1, it will come here. If carry flag is not 1, it will come here. That means if next instruction, if b2 actually means bit 2, bit number 2, b2 of al equals 0, it will come to the next line. If it is if b2 of al is 1, then actually it will come to, it will do a jump, and it will come here in this line. Is that okay? Okay, so these are the things. It's called the if then structure. That means if something is true, it will perform the jump, otherwise it will go to the next slide. It's like that. Okay, so now you know we have some structure It's called repeat until structure. What is the flow chart for this repeat until structure? For example, you start, this is the beginning of your program, then you initialize the counter. Can you remember we set the counter? Like for 5 times loop, we set the counter cx equal to 5. So something like that. You initialize the counter value, and then here you will yeah, your program loop program, it is start here and then decrement the cx, a counter, I mean counter, you do counter is reduce 1, and then loop done. That means if cx is not 0, if it is not 0, it will go again, it will go ahead again. And if it is true, that means cx is 0, that means you will go to the next, out of the loop. So it is a loop, right? It's a loop structure. That means, so this is called repeat until. I mean, counter is initialized first, and then end of the loop instruction, the counter value is 1 down, and then you check. If it is not 0, it will continue the loop. If it is 0, then it will out of the loop. This is called. Let's see the example. For example, move cl comma count, it may be 10, for example, 10 number you have, cl comma 10, and then next line is this one. And so that means you will do some operation here, and then there is a decrement cl. So decrement cl, that means counter is now 1 less. Okay, you reduce it by 1, and then if it is not 0, if counter value is not 0, it will come here again in this line. So this is the loop. But you can remember, I said you, these 2 line can be replaced with one instruction, one line. What is this one? This 2 line decrement, I mean, you reduce the counter by writing your instruction, and then said jump not 0, do again. Or yeah, but these 2 line actually, how can we replace? What instruction we use? You can, we already use in the lab and in some programming example. Can you tell me? Nobody? So can you remember we use this one? Yeah, loop, and then loop is not all, where actually it will go again. Okay, loop again, again, because our label is again, name is again. You can write name, whatever it is, doesn't matter. So that means this 2 line is the same as loop again. Yeah. So yeah, R or whatever it is, because here the label is again, so that's why we use loop again. Okay, so that means what actually is done by writing the loop again is the same as these 2 line. This is, I mean, counter will be decrement by 1, and then it will check a condition. If counter value is not 0, then it will continue the loop again. Otherwise, it will go to the next line. Yeah, that means it's called repeat until. So this is a loop instruction. It's in the way it is called repeat until. But there is another format. It's called while do. In a while do and repeat until, its structure is a bit different. What is the different here? First of all, we start the program, then we initialize the counter, and then what actually do? We decrement the counter in the beginning. We decrement the counter beginning the loop instruction. So then we check that if the counter value was 0 or not. If it is 0, that means come out of the loop. If it is not 0, yeah, perform the loop operation. These are the loop op. This is the loop operation. I mean the instruction related to inside the loop, and then the, yeah, you decrement oh no, sorry, decrement is done at the end, but at the beginning actually we check that the count value is 0 or not. Okay, so we do not check it at the end, we check it at the beginning. That's the difference. And then we come here, repeat until repeat. So our condition is checked at the beginning, not at the end. If you look at the structure, I mean example, move CL comma count B, for example 10 5 whatever it is, and then at the beginning we check the condition if it is 0 or not. If jump 0, it will come out of the loop instruction, it come to this level. If it is not 0, it will work here. These are the things are loop instruction, the instruction that actually we want to do. And then we decrement the counter again and then jump again. So it is not condition actually, because it is an unconditional jump. All right. That means in a, what is the difference? What are the differences between repeat until structure and while do structure? One thing is I mean the condition is checked at the beginning in while do structure, but in repeat until condition is checked at the end. And other thing is, other thing is in a while do structure we have two jump. One jump is at the beginning of the loop instruction, and one jump is, this is not a uh, unconditional jump. Unconditional jump at the end of the loop instruction, and it is unconditional actually. But conditional is one, it is at the beginning. But in a while do structure, there is only one jump and it is conditional at the end. So these are the things actually basically. So is it okay? Do you have, is it clear to you that what is the format of while do and what is the format of repeat until? Okay. Okay, now it's about, look, this one actually we use in our program. I mean in the lab too, a block move program. Block move program means we have a set of data, we move them from one memory location to the another memory location. So like for example, if you can remember, we have a in experiment we have a set of data. That's why it is called block. A block of data, a set of data. Okay, so for example, so and yeah, so this is our source data. Source data, for example, it is the name of the variable is ELK1 A. Okay, and here is okay. So look at here. We have a source data. It is the beginning with the name BLK1ADDR. Just for example, it can be X, it can be Y, whatever it is. For example, BLK according to this example. Yeah. So we have a few data here. We have a few data here, for example. And then, so this set of data, we want to move them from here to this location. Here. So the name of the this memory is BLK2ADDR, or with the name of this one. So what actually we do here? First of all, we initialize the data segment. Move X comma data at the data segment ADDR, or at the rate data, if you can remember. So like instead of this one, at the rate data. for example. It is not the whole program actually. It is just part of a program. Main thing, just to give you the idea how actually we do the do this operation. I mean, we move a set of data from one memory location to another memory location. So this one already we use. So this two line is for initialize the data segment. Okay, move ax comma at the rate data and then ds comma x. Okay, now then move si comma block 1 attdr because the name of the data is assigned to a variable block 1 addr. Okay, so yeah, and where actually we will move it, the another variable name is block 2 addr. So this one is blk, so it may be x, it may be y, so it doesn't matter. Okay, then how many data we have? For example, n data, and n can be 10, 5, it depends on what is defined in your what actually you are going to do n. And then move ah comma square bracket si, ah or al, whatever you want, doesn't matter. For example, ah comma square bracket any register you can use, ah comma square bracket si. So that means square bracket means memory location. What is the offset of the memory location is defined by si, and what is si? Si actually representing the offset address of the first location. For example, the here the memory data is 15h, 15h. Okay, so that means the memory location data will come to the ah. So that means 15h is now ah. 15, it is now in it is now loaded in ah, and then move square bracket di, again memory location comma s. So that means the value of ah will come to the memory location represented by offset of the memory location is represented by di, and di you know that di is represented by this memory location offset, this memory location block 2 addr. So that means now 15h will come here. Is that clear? Is it okay? This one, this data is now moved here. And then what actually do? Yeah, this is actually we explain in lab 2. But again, because here actually I mean we'll use the jump instruction, we'll use the loop instruction, kind of like that. That's why. So then again increment si, because we have to go to the next memory location. We have a set of data. We have to. It's not like one data. It is a set of data. It may be 10 data, 5 data, 6 data, something like. Our next data is, for example, 26h. Okay. So that means then, so si actually was indicating the offset of the address of the first data. Now we say increment si. That means si actually have the si has the offset address of the second data. Okay. And di also was was holding the offset address of the first memory location where actually we will move. Now we increment di. That means it will hold the second memory location. Okay, and then we decrement the counter. Decrement the counter cx. If it is not 0, it will come here. Again do the move ah comma square bracket si. Now si is not the first memory location offset. First memory location indicating. It indicates the second memory location. So now it will take the like 25h. So 25h. Okay, 20h for example. 20h in ah. Then we say move square bracket di comma ah. That means it will come here. 20 will come here. All right, and then it will continue until when actually cx becomes 0, what will happen? It come to the next line. And next line is like we say halt, or we say for example end, or whatever it is. So next line it will come out of the loop. So this is the thing. But these two line actually, so for basic understanding we can use this two line, but for simplicity we can use this line. Instead of this two line we can write loop n x t PET. Is that okay? Is it clear? Is it okay? All right. So this is called yeah. Here actually we can see few things we use here. One is called conditional jump instruction. One is called, instead of these two line, we can use the loop instruction. And one of the thing is like, in what format it is? It is called repeat until. Repeat until. That means do the things until counter value is 0. So it's like that. So it's a loop instruction, but we can say the structure is repeat until this format. But we can write it also in, while loop. Repeat until is one format. Also, we can do the while loop format. Okay. Let's see another example. For example, it's a implement an instruction sequence that calculates the absolute difference between the content of AX and BX and place it in DX. Okay, absolute difference. AX and BX, two value in AX and BX, two register. So if AX greater than BX, so what is the difference between these two? AX minus BX, because you have to take the difference and absolute value of absolute value of difference. AX minus BX. Okay. So, so if AX greater than BX, so AX greater than BX, then it is okay. But if BX greater than AX, what will happen? So if BX greater than the difference should be BX minus AX, right? BX minus AX. All right. So, so that means AX and AX minus BX. So yeah, that means we have to understand that if AX is greater than BX, then AX minus BX is fine. But if BX greater than AX, then BX minus AX should be done. Because if we want to calculate the absolute difference, okay, absolute difference, then yeah. So so compare AX comma BX. If when carry happen, if BX greater than X, right? No carry happen if AX greater than BX. So if AX greater than BX, we will perform AX minus BX. So then actually, so that means if no carry, we will come here, move DX comma AX value is moved to the DX, and sub DX comma BX. So that means DX has AX actually, basically. So it actually perform AX minus BX and result will be saved in DX. Is that okay? Do you understand this two line? This is okay. This two line. Yeah. So now, yes. So then after doing this, we say jump down. It will come out of the loop and it will come at the next out of the yeah, NOP. NOP means no operation. So whatever, just no operation or something like end, for example, end. Okay. But if actually if BX is greater than X, what actually will do? There will be carry happen. If carry, it will do a jump. It will come to here, DIFF2, difference 2, for example. Now here, what actually do? We have to do BX minus X. So that means BX will be set in DX register now. Move BX comma DX, sorry, DX comma BX, and then sub DX comma AX. That means we will do BX minus X, and result is saved in the DX. Then next time. So is it clear? Is it okay? Yeah, so that means here actually these are the very basic thing, but it's just helping us how to use the jump instruction, conditional jump instructions, and something long in assembly language. All right, so now sometimes, you know, like we write in our program, our main, we may have a sub-program also, sub-programs or subrouting. You know, this idea actually you got it in C programming also. The subrouting or sub-program, whatever, same idea, same thing. So a subrouting is a special program that can be called for execution from any point in a program. I mean, so if like a part of a program that actually we use quite often anywhere from anywhere, then it's better to write it separately. Like for example, if you can remember, if you, I mean this, if you can, I mean, recall the idea. For example, this is our main program, and a sub-program that actually we may have to use quite often. So we write it separately here. This is the, for example, subrouting or subprogram A. And okay, what actually we do in the main program, we are moving on, and then we say call subrouting A. We have to I mean, in assembly language, we have to instruction, a special instruction is called call, C-A-L-L, call subrouting A. That means you actually jump from this main program to the subprogram here. When you finish, then you have to use at the end, at the end of the subrouting, you have to write a return, another instruction. So here actually that is in a main program we write call, and in a subprogram we write return. What does return mean? Return means you actually from here to the, you will move to the next line in the main program, because the line from where actually you do the jump, you have to go back to the next line. Is that okay? Is it, do you understand this one idea? The subprogram or subroutine? Okay, so now for example, we have, then we move on. Then again in our main program we have, and we want to use the subprogram again. Then we say, for example, call subprogram or subroutine A again. So that means it will, from here it will do the jump here in the first line of the subprogram. Then at the end of the subprogram it will perform the return. So return means it will come out to the next line. So this is the idea, basic idea. That means here actually what actually we have seen that we in a main program we have to write the call instruction. In a subprogram we have to write the return instruction. So these two are new idea for us. So call actually we write it C-A-L-L, and return we write it in a R-E-T. R-E-T. So R-E-T means return, for return. So a so that means what is subprogram or what is subrouting? In assembly language actually basically it is called subrouting. So this is the same thing as subprogram. In C language we normally use the subprogram, we call it. So a subrouting is a special program that can be called for execution from any point in a main program. So a subrouting also called a procedure also, you know, so it is also called the procedure also. So a return instruction must be included at the end of the subprogram to initiate the return sequence to the main program. Yeah, that's it. This is I said you. So we normally use the call and return, but sometimes also we use, like, you know, during the stack operation, I mean stack idea, we use this push and pop. If you can remember, we use this push and pop. Sometimes we may have to use this push or pop, so to save some I mean to save the, you know, to save some register value that may not, that may be, if we do not save them, they may be changed in the subroutine. Okay, so that's why push and pop, so to save them temporarily. What is the purpose of the stack register? Can you remember? In also in a measure one, you got what are the functions of different segment in memory. So a stack is also one segment of memory. What is the purpose of stack segment? We keep the temporary. It is used for temporary save of data and return address. Return, and also sometimes, you know, when actually we do the call, for example, we jump from this line to the subprogram, the return address must be saved in. We don't have to save it manually. It is by default, it is saved the return address. Otherwise, actually, it will be lost. It will do the jump here, but then it cannot back to the next line if it doesn't save the return address. So that means return address during the jump or subprogram call, subprogram operation, it saved the return address, okay, in a stack. So by using push and pop actually, but sometimes we also write the push and pop instruction to save the some register value in a stack for temporary. Then we can take it back. Okay, so these are the, so that means, so here actually what actually we have seen here, there is one thing, it is called subprogram or subroutine or procedure. It's the same thing. So it is what it is a set of instruction, or it is a special program that can be called for execution from the main program anytime, from anywhere. Okay, from any point of the main program, or for any time, maybe twice, thrice, something like that, 4 times, 5 times. Okay, and in a main program we have to write call, and in a end of the subprogram we have to write the return, ret. And push and pop also related here. Sometimes we use these instructions manually, sometimes it is done by the microprocessor internally. Okay, so now it's about the how actually we have to write the procedure. You know, we have to put a name here, name, like for example, if you can see for example, yeah, write a procedure. Look at the examples, then it will be more understandable. Write a procedure, name is square. So what is the name of the subprogram or procedure? For example, its name is square. What is the what actually you will do in this procedure? It squares the content of BL. So like if you have BL has 2, it will do the square, that means 2 square, that is 4. And where the result will be saved in BX. So result will be saved in 16-bit, but the previous data is in BL, is 8-bit format. So okay, let's see. So for example, so what is the name of the subprogram? So for this is the square. Then we have to write that PROC. PROC means procedure. Procedure is shortly we write it PROC, and then we have to write either near or far. So that means there are 2 types, near or far. I mean, this subprogram, is it in the same segment of the main program, or it is in the different segment of the main program? It is like that. So near means if this subprogram is in the same code segment of the main program, that's why it is called near. That means it's not very far. Okay. Then we for example, in the procedure we say push AX. That means AX, the value of AX in the main program we have we use the AX. Now in a subprogram we may have to use the AX again. So that means that's why we set the previous value in the stack, push AX. That means so that it doesn't change. And then move AX comma BX. So yeah, BX is now AX, and then IMUL, integer multiply BL. So what will happen now? Look at here. So what actually we have done in this line, move AX comma BX. That means actually AX equal BX, right? AX is the same, will be BX. And BX has, so that means we can also say AL also same as BL. Is it okay? BL value is we set the BL value in AL. Is that okay? AX equal BL, BX is the same like AL equal BL or and AH equal BH. Okay, so because our data in BL, so now we keep it in AL and then multiply I multiple BL. That means AL times BL. AL has BL. That means BL square. It happens the BL square. Okay, it performs the BL square. It performs the square of the BL. And but result is saved in AX. Okay, so the result is saved in the during the multiplication. The result is saved in AX. So now we say this AX will copy to BX because our result should be in BX, and then so then we say pop AX because AX is use of AX is done. What was the previous value of AX? We keep it in stack using the push, and now we use the pop AX. That means restore the AX register value and then return RET return. So return from the procedure, and then but we have to finish it by formally with the same name square and then end, but at the end we have to write P for procedure, ending of procedure. So do you get the idea about how to write a procedure with an example here? Is it okay? Yeah, so that means we have to, first of all, we have to put a name. Then we have to put, for example, here we name it a square, and then we have to prop for procedure, and either it can be near or far. If it is within a same segment, it can be rear. So normally, if our program is not too big, then it is near is okay, because it will not. We don't need the two code segment. Okay, and then push because we have to use the AX here again. So that's why the previous AX value we have to save it by using push, and then we return it back using pop. So push and pop. Okay, so we restore back the AX value. Okay, but in between, what actually we have to do? We have to perform the BL square. So BL, so that means maybe you can write move AL comma BL. That is also fine instead of AX comma BX, and then I multiple or MUL also you can use multiple BL. So that means it will AL times BL, but AL has BL already. So so that means it actually perform the square of BL. So result is saved in AX. So now we copy the AX value to BX value, AX value to BX value. So that means result. Then we return from this is we return from this procedure. That's it. Okay. So is that yeah? So this is an example about how to write a procedure. Okay, now there are some loop instructions. One is called LOPP. This one we already use it, and sometimes also we can use also loop equal, loop while 0, yeah, and loop not equal, loop not 0. So the actually if we already familiar with LOOP loop. So if you can remember in a loop instruction, what actually we set the we set the counter at the beginning, and then at the last end we say loop next. How long it will continue the loop until CX value becomes 0, counter value becomes 0. So loop in X actually is the short form of two line. Actually, one line is decrement Cx, decrement Cx. One line is short form of decrement Cx, and another line is what? Jump not zero, and this label. This label is next. Okay. Sorry. So this two line is the same as this one. Okay, so a loop next. Okay, so this is already we say this two line we can replace it with just one line loop instruction. Yeah, can you remember the just we write a program, a set of data, a set of from a block move program, a set of data from one memory location to one another memory location. So these line are, so instead of this one we can write it at the rate data, at the rate data. Okay, and then okay, and then move ds comma ax, move si comma, everything is okay. But here, look at here, we use the loop instruction instead of this two type of line. Instead of this two line, we can use just only one line loop. This is actually I said you right. Okay, so this loop instruction is clear, right? We already use it, even though it is already. Is that okay? Is it okay? Are you clear about the loop instruction? Okay, all right. Do you have any exam today? Which exam? At 12. Okay, okay, 370. Okay, okay, okay. All right. So then, I mean, okay. So then, okay. So I can finish now. I'll not go anymore. So okay. So take your time for the for the exam. Okay. All the best. Any question do you have?